Welcome back, everybody. Thank you for tuning in to Mr. Lavert's YouTube channel one more time. This is the last new calculus content for the year. You will not see me again on video. Actually, no, that's probably not true. I'll probably post review videos for the exam and whatnot. Just so you guys are aware, and it's good that I have this going on the video, the schedule of events for the rest of the year. So today we are doing section 6.1. Tomorrow we are I'm hopefully going to get through all the notes today, just a couple of slides. Tomorrow I'm going to let you work. Thursday I'm going to let you work. Friday we will review. And then I know I hate to do this to you guys, but on Monday we're going to do our 5.5.6.1 test. One day. I can't put it on Tuesday. It's a one-day test. I can't put it on Tuesday because it's another late start day. I can't put it on Wednesday because it's another late start day. I can't put it on Thursday of next week. You want to know why? Senior walk. That's your senior picnic and your senior walk thing. I can't do it on Friday because that's just way too late. And by that time, you need to start reviewing for the exam, right? Because then the next week, by Wednesday, you'll be taking your exam. So I got to put it on Monday. Very sorry. But you will get your week from today. You will have your exam review in your hands. Be studying for the exam. Yes.
So if we're taking the AP and AP test on Monday, should we just come in like another?
Yeah. Honestly, I think what I'm going to do is really I want your tests done over the course of Monday, Tuesday, or Wednesday, because I know a lot of people are out for AP tests on certain days. Just know that if you're going to be out on Monday, try to come in during the lunch period on Tuesday or Wednesday, because those are not shortened. Don't try to just take it in the class period. Does that make sense? And we'll schedule that whenever. All right, so here we go, section 6.1. You know how back in the first semester we learned about the derivatives, and then we learned all about application of derivatives, right? This next portion of material is, we learned about integrals, and now we learn about the application of integration. But unfortunately, we ran out of time in this year. So we are really only going to be looking at one application of integrals, and that is finding the areas between curves. If you choose to pick up here and take Calc 2, you will probably get into the rest of Chapter 6. They will probably start fresh and maybe review some of Chapter 5 as well. But Section 6.1 is all about areas between two curves. Areas between two curves, and how to use integration to find the area between two curves. Now, taking a look here. In Chapter 5, we defined and calculated areas of regions that lie under the graph of functions. Like, for example, let me put this on the big board up here. If I have some function, okay, if I have some function, f of x, right, this is f, we defined the integral from a to b of f of x to be this area, right? That's what the integral. That's what it means to be the integral of f of x from a to b. So now what we're going to do here today is say, well, what if I've got another function, g of x? How do I define this area? Oops, let me put this in purple. How do I define this area? How would you geometrically define that area? How would you define that area? F minus g. You would take the area of f of x and take away this little chunk, right? Well, what is that little chunk? That is the integral of g of x from a to b. So, to find the area in between any two curves, you literally just take f of x minus g of x. Now, you can do that separately. You could take the integral of f, the integral of g, subtract them, or you could take the integral of the total f of x minus g of x, if the functions are really easy to put together, okay? So take a look at these diagrams here. You might be thinking to yourself, wait a sec. Isn't this a negative area? How's that going to work? Well, f of x minus g of x, I want to add on this area, don't I? What's that area going to turn out to be? Negative, right? That area is going to turn out to be negative. And when I minus a negative, what does it do? Adds. So we can actually keep that same operation, that f minus g, because even though that's going to turn out negative, it'll end up adding it to the original area anyway. And then look, I've got this area here that I would want to subtract away. That area is going to stay positive and will subtract away off of the area of that. Okay. All right. So here is our formal definition of how to find the area between two curves. How to find the area between two curves. And honestly, you could separate them, or you could make this one big statement. It's honestly going to be easier if we keep it as one big statement. The integral from a to b of f of x minus g of x. You just find the difference of the two functions. Then you find the integral of that, whatever that is. Don't forget the dx. Do that. Anybody in here need to take their part? What? Just Reagan and Son, right? All right. That's all the new notes for today. All the rest of this is just problems. Yeah, pack it up, pack it in. And that's it for the day's video. No, just kidding. All right, let's take a look here. Find the area of the region bounded by y equals e to the x, bounded above by y equals e to the x, and bounded below by y equals x. Now, you may be thinking, well, how do you know what f of x is and what g of x is? How do you tell the one function from the other? How do you know which one comes first? Because if, subtraction is not commutative, I can't change the order. That's not allowed. So f of x is always going to be the top function, graphically on the top, right? The one that's above the other function. So f of x is always going to be the one on top. G of x is always going to be the one on bottom. Top minus bottom, like always. Okay, so now let's graph this real quick, though. Just to be sure, I am told that y equals e to the x is on top. I am told that y equals x is on bottom, but let's double check that. Let's think about y equals e to the x. What's the y-intercept of e to the x? If I plug in 0, it'd be e to the 0, so 1, right? So here is my y-intercept, and it's generally going to take this shape, right? An exponential function, base e. Okay? Y equals x. That's just, 1 comma 1, right? 0 comma 0. Chase him down. Yeah, chase him down.
I didn't even know.
You gonna let him walk free like that?
I didn't. Why are you yelling? Yeah, I didn't know he was gone.
What do you do? You want to make a push right now? What's come out?
I don't calculator. I don't even have my backpack. They wouldn't let me go get my backpack.
I got your pencil. Here you go. Get your calculator.
Okay. Do I have enough time?
Where are you at 8th period?
Chemistry.
You don't need chemistry. No, you just take tomorrow. All right, so now what we're going to look at here is this. Okay, here's 1, here's 0. I am going to find the area of that purple region. I'm going to find the area of that purple region. And I do that by finding the integral from 0 to 1, a to b, of f of x. Now, in this case, f of x is e to the x minus g of x, which is y equals x dx. And that is actually a pretty easy integral to solve for. I don't even need any substitution. What's the antiderivative of e to the x? E to the x. What is the antiderivative of x? X squared over 2, and I'm going from 0 to 1. Plug it in. That is e minus 1 squared over 2 minus e to the 0 minus 0 squared over 2. Okay, so that's going to give me e minus 0.5, 2.28, minus, now, e to the 0 is 1, again, right? 1 minus 0. So really just minus 1. 1.22, if you will. That's that purple area. Okay? Top minus bottom on the graph. Pretty simple. Not too bad, right? Let's do another one. Find the area of the region enclosed by the parabolas y equals x squared and 2x minus x squared. Now, am I told what's on top and what's on bottom? Am I told even the parameters to go from for my definite integral? No. So I guess the best thing to do would be to graph this. Let's graph this. Let me turn the plot 1 off there and say I've got x squared, so just my standard parent quadratic, and then 2x minus x squared. I'm going to zoom 6 to put this into my 10 by 10 window. Okay, I'm going to zoom in a little bit because I see the enclosed region. It's just really small in there. Zoom in. Zoom 2, enter. Okay, so this is the region. Hello? No? Okay, cool. So that's the region I want to try to find, right? That enclosed region. Now, here's the deal. Do I know where I want to find my A and B yet? I mean, I can kind of guess. Oh, there it is. I can kind of guesstimate it. It's probably 0 and 1, I bet. But I'm not sure yet, right? That's the area. So let's figure out those intersection points. I could do this on my calculator. Oh, I just did it. It was 0. Oh, there it is. And then choice 5, first curve, enter, second curve, enter. I just have to guess up here. It was 0 and 1. Okay. But I really didn't need my calculator. Because watch, I just want to know when 2x minus x squared equals x squared. Right? I want to see where they intersect. Basically setting it up like a system of equations. Add the x squared, subtract the 2x, excuse me. So 0 is equal to factor out the 2. Throw back to algebra 1. 0 is x. 1 is x. So yeah, 0 and 1 are my intersection points. So that tells me that I want the integral from 0 to 1 of, now what function is on top? 2x minus x squared. Minus, what function's on bottom? That's x squared. Right? Is there some simplification to do before I run my antiderivative? Yeah. So I'm just going to make this from 0 to 1 of 2x minus 2x squared dx. Now let's run my antiderivative. Okay, now let's run my antiderivative. So that means I've got 2x squared over 2 minus 2x to the third over 3 from 0 to 1. The 2's are going to cancel, right? And forgive me for not writing the whole thing out again. All I want to do is plug in 1. The nice thing about this is it's going to 0, right? If I plug in 0, it's going to completely go away, right? So this is going to be 1 minus 2 times 1 to the third, or 2 over 3. 1 minus 2 thirds, it's 1/3, or 0.3. So I know the area enclosed by those regions, or enclosed by those graphs, is equal to 1/3. Let's do another one, shall we?
Is there like a real life application to this?
Yeah.
What's the real life application? I'm curious.
If you had to, compute the area in between two curves in your real life test next week,
Well,
that's real life. That's real life, man.
How does
That is real life.
How does this help me be more competitive in the job market?
Because you can say, I passed calculus.
You get a 4.0.
Yeah. Find the area of the region bounded by the curves y equals sine x y equals cosine. I had to be weird. I had to put a trig in there. Y equals sine x, y equals cosine x. All right, now, we could graph
You okay?
sine and cosine by hand. I did that second period. No thanks. I'm just going to go in here and say sine x. Oops, that's sine squared. Sine x and then cosine x. Okay. I want to go from 0 to pi over 2, right? Let's manipulate my window a little bit. Let's go from bottom to top. We know it's going to range from 0 to or from -1 to 1. So let's let my y values go from -2 to 2. And let's go for my x values. Let's say, let's go from -0.5 to get just a little bit to the left of 0, and then just a little bit to the right of pi over 2. Let's go to just pi. Okay, so what are we trying to do here? Well, we are trying to find the area from 0 to pi over 2. Now, where is pi over 2? If this is cosine, where is pi over 2? Where it crosses the x-axis. Because think about it. What's the x coordinate? Oh, sorry, up here at pi over 2. What's the x coordinate? 0, right? So cosine has a 0 at pi over 2. And it only makes sense that this is the coordinate 0, comma 1, right? So this maxes out at pi over 2 as well. So that's telling me this is at pi over 2. So I want to find the area of the region bounded by these curves. What is that saying? Find that total yellow area. Now, I have to take this in 2 separate pieces. Because think about it. What's above and below? Doesn't it change halfway through? Halfway through, I mean, it starts with cosine being on top, right? You know, all the way up until here, it is the integral of cosine x minus sine x dx. And actually, I need to make a little bit more room and bring this down here. Right? That is this piece. Whoa. That is this piece. Now, what are my boundaries? From 0 to pi over 4. Why pi over 4? Because don't they have the same coordinates at pi over 4? Radical 2 over 2? Now, I want to add that with the area of from here to here. The integral from pi over 4 to pi over 2. Now what's on top? Sine. Sine x minus cosine x dx. And we can find that area. That's not too bad. Okay, what's the integral of cosine? Sine. What's the integral of negative sine? Cosine, positive cosine. Okay. Plus, what's the integral of sine? Negative cosine. What's the integral of negative cosine? Negative sine. From pi over, that's a pi right there. Pi over 4 to pi over 2. Sorry. Poor Amos. And now we plug it in. Okay, I've got sine of pi over 4 plus cosine pi over 4 minus sine 0 plus cosine 0. So this whole first chunk is 0.414. Let's see what the whole second chunk is. Okay, I've got negative cosine of pi over 2 minus sine of pi over 2, negative 1, minus negative cosine. Actually, I need to put this in parentheses. Negative cosine of pi over 4 minus sine of pi over 4. Another 0.414. So all said and done, 0.828. So sometimes you will need to split it up into between two areas. It doesn't look, these are just homework problems. Like I'm just gonna take these out of the homework. I'll just do these tomorrow. Sound good? And then you just won't have to do them within your homework. Sound good?
Sounds good.
Last new video lesson, at least. So long, everybody.
Bye.